Today, I'd like to introduce my work trying to reveal the neural representation of content and structure in auditory sequence memory. As memory is formed by organizing independent events based on their specific order in which these events occurred. Not only the events themselves are important, but also the order. Once the order information is disrupted, formed memory would turn into a mess. Thus, in order to memorize a temporally structured experience like a piece of melody, we need to store two types of code in our brain. The first one is the content code, which is the frequency of each tone, and the other one is the structure code, which is the ordinal position for each tone. Only if you have both the content and structure code in the brain, you can remember the piece of melody successfully. How the content code is represented in the working memory process has been examined by some research. However, this is not the situation for the structure code representation. Thus, I want to investigate how the structure and content code of an auditory sequence are represented in the brain when participants are performing a delayed match-to-sample working memory task. Now, let's first look at the task. 3 pure tones with different frequencies were presented, and participants were required to memorize both the frequency and the ordinal position of these 3 pure tones. And then a ratio cue would be presented, indicating which tone's frequency would be tested at the end of the current trial. Here, the ratio cue is 2, which means the second tone's frequency which would be tested at the end of the trial. Then, in the subsequent delay, a white noise would be presented, aiming to perturb their hidden network and reveal their content information during their maintaining period. Lastly, a target tone would be presented, and participants were required to make a judgment on their target tone's frequency was higher or lower compared to their cue tone's frequency. The brain activities were recorded using EEG when the participants performing the task. Then let's look at the results. We employed a time-resolved representation similarity analysis decoding method to investigate whether there exists content code and structural code in the brain signals. We use the beta value as the index of decoding accuracy. The higher of their beta value, the stronger the corresponding representation. So we can see there exists content code and structure code during encoding period. The representation of tone's frequency emerged shortly after tone's onset, and the representation of tone's ordinal position occurred even before their onset of their tone. Actually, this is reasonable as the ordinal position of the tone indeed could be formed prior to the appearance of their tone. In addition, we conducted the decoding of content and structure code independently with each other. So we can see these two codes, the content code and structure code, are factorized represented in the brain during encoding period. Then let's move to what happened during maintaining period to see the memory-related representation. As we only conducted the decoding for the content and structure representation, for the content and structure representation for the cue tone, the maintaining period was divided into 2 phases, one after ratio cue and the other one after white noise for illustration purpose. Now let's look at what happened after the ratio cue. So we can see there only exists a structural code after the ratio cue, but not for their content code. In contrast, there exists only content code after the white noise, but not for the structure code. So we observed double dissociation of content and structure code during maintaining period, which indicated these 2 codes are also represented in a factorized way during maintaining period. So we come to our first summary. There exists factorized content and structure code during encoding period. A positional ratio cue during maintaining period activates structure information but not content, and the auditory white noise during maintaining period triggers content response but not structure. And after having observed content structure code during encoding and maintaining period. We want to see whether the code during these two periods are similar. So we conducted a cross-temporal generalization analysis using two methods. The first one is the representation similarity analysis. The other one, as we can use before, and the other one is the logistic regression models. And we can see both of these two methods shows significant generalization of structural code, which means the structural representation remains unchanged during throughout the memory process. In contrast, no significant generalization was detected by both of these two methods, which means the content code undergoes a transformation throughout memory process. Lastly, we want to evaluate. Lastly, we want to see whether the neural representations held in working memory has behavioral consequence. So we compared the representation for trials, with correct response with the representation for trials with wrong responses. We can see significant difference occurred only for the content code during the maintaining period after the white noise, but not for the structure code during maintaining period after the retro queue. And also there is no significant difference for correct and wrong trials for the code during encoding period. So we can conclude the content instead of structured information maintained in working memory is largely correlated with recalling memory performance. And this is not due to initial sensory encoding. Now let's summarize our findings. In an arbitrary delayed match-to-sample task, we found dissociated neural codes showing largely distinct characteristics for structure and content information. The structure codes representing somewhat high-level and abstract information of the stimuli are kept constant throughout the working memory process. In contrast, the content code for specific sensory properties are transformed from encoding to maintaining period. The structure and content codes are represented in a factorized way, which could benefit for applying structured knowledge of new sensory input to form new memory effectively and efficiently. Thanks for your listening. That's all.